see here. So I've been given the not so easy task of trying to give you a little bit of background on virtual tabulation, which is the patented approach that Configit has taken to solve the configuration problem. And as Enya said, if you have questions, please just submit them in the panel on the right, and we'll collect them at the end, and hopefully we'll have time to answer all of them. Otherwise, we'll give you feedback later. What I will go through right now is basically what is the configuration problem, why is it difficult. I'll touch upon how this problem has been addressed previously with different technologies. And then I'll spend most of the time on explaining what is this VT approach that we have taken, and what is it that once you have embarked on that, what types of analysis can you do, and what possibilities does it give you. So first of all, configurable products, hopefully we are all on the same page what that is. Basically, we deal with products that you need to configure in order to buy them, to order them. A very typical standard classical example is of an iPhone. You need to choose things like colors and capacity. Now, a phone is a fairly simple product when it comes to configuration, even though there probably are some parameters we don't see. There's only a small handful of parameters you need to choose. Maybe a little bit more realistic example would be something like a chair, where you can choose different materials and different seats and stuff like that. But even a chair is from a complexity perspective, from a configuration perspective, also a fairly simple product. It will have maybe 10 configuration parameters. The types of products we normally deal with in Configit are much more complex. They could be cars, could be complex machines, where you have hundreds, if not thousands, of parameters that you need to configure. I would like to point out also that it doesn't necessarily have to be a physical product, but it could be a service or an insurance or a contract. All of those that potentially can be configured. The background for being able to configure a product is that you introduce what we call product models. These are a model which define the variability. It defines the configuration parameters and the rules. So, and it's sort of the backbone of being able to support the different functional areas that you might have seen before in our CLM circle here. So the modeling in the center here, the product models, are the foundation for doing pretty much any types of analysis and optimization of configurable products. The basis for a product model is that of features. So we deal with the variability in terms of not parts, but slightly more abstract entities that we sometimes call features or options. An example could be the color of a car, as shown here on the left, where you have a choice between different paint colors. And it's pretty clear that that's not a product, or sorry, a part as such. It will influence a number of different parts on the finished product. It is a variability that the customer will have to choose before we can manufacture the product. On the right, we have another example, again from a car, but and that could be what type of interior design you would like of your car. And then on top of these features, we have the rules, and the rules can come in many different shapes and forms, but they basically restrict the combinations between the features of our product. And I will not go into how to express these rules, and it doesn't really matter. The foundation is just that the rules are eliminating certain of the combinations. They express that there has to be some relationships between the different features of the product model. So let's take a very simple example, and I'll use this throughout this little session here. Here we have a very simple product model. It's a bicycle. It consists of 4 different what we call feature families. We have warranty, material, region, and color, each with a number of choices that we can select. So we have a color that can be red, green, blue. We have a region, North America, South America, and so on. And this is the 4 configuration parameters we have in our product model. And there are a number of features in each one of them. And then we can imagine that there are some rules on top of this. These rules are a little bit made up, to say the least, but you can imagine that if you pick the aluminum material, then you cannot get the color to be blue. And it might be that there's another rule that says that in Asia you can only get the aluminum. Those rules will restrict the combinations of these choices you can make up here. Given a model, we deal with a configuration, which is a selection of choices or features to each of these parameters. And here, and once you've done that, you have produced what we call the feature string. And the feature string is this selection. We think of it as the DNA of the product. And once you have that, you can generate and derive the bill of material, different types of product codes, maybe documentation. You have all the information that you need in the different functional areas of the organization to deal with that particular configuration. And just to make it a little bit down to earth, on the right here is shown a piece of paper that was in a car I used to own. It's an Audi A3, and this is the exact feature content of that particular vehicle. With that little piece of paper, I could go down to Audi and they would be able to produce exactly a car that was just like the one I had. So what is configuration? Well, once we defined our product model, we want to support a process in which a user is guided to find a valid configuration. So a valid configuration is one where all the rules are satisfied. And that's sort of the core and the fundamental of the configuration problem. That is, how do we guide a user? How do we find a valid configuration? One that where all the rules says yes, and we have filled out something for all the different configuration parameters in our model. And the UI for doing that could look very differently. Here are a few examples. A classical car configurator, it might be a scanner from Philips, or it might be something from our own quoting tools on the right here. That's a little bit more internal and technical. But they all have the same fundamental interaction. User selects a parameter. He needs to know what are now my choices moving forward. It seems like a very simple problem. It doesn't seem like that should be difficult for a computer to solve or help a user do this, but it turns out it is. And that's probably the first sort of step I want to take here. That is to say, if you look at this from a computer's perspective, from a computer science perspective, then it turns out that the most fundamental question you can ask, which is, does a given product model have any valid configuration? I don't forget about guiding a user. I'm only interested in, does there exist a configuration? Doesn't matter which one, just is there one? That problem is called a SAT problem. And I have a link here, and we'll share these PowerPoints later, but you can find what this is by going to Wikipedia. And this is a completely standard definition of a computer science problem of finding a satisfying assignment to a Boolean expression. Now, it turns out this particular problem is what's called NP complete. Again, I don't have really the time to go into what this means, but it's a class of problems that is well defined, and scientists have studied it for a long time, and they know a lot of properties about this complexity class of problems. And it turns out that the consequence of this problem being NP complete is that we can prove that there is no efficient algorithm that can solve this. And it's a pretty annoying fact, but that's just how the world is. It means that there are scenarios that will be take exponential time in the size of the problem. And that goes no matter what approach you take. So that's just sort of a mathematical fundamental of the problem. So, and I've put in a little video here on the right, which explains this fantastically. I think anybody who has any interest in complexity analysis and just understanding this slide more should spend the 10 minutes to look in this video. It's very well made and very easy to understand. It's not very technical as such. So this is just the you could say the world as it is, and there's not much we can do about it. So that doesn't mean the problem goes away. So over the years, people have tried to solve this in many different approaches, And I've tried to highlight the top level, or sort of the most general approaches that have been taken out there. The most first approach was called rule-based systems, or production rules-based systems, and this goes really back earlier than the 80s. Really, it goes back to the 70s. There was a famous deck configurator for a computer where they used this, and it's a very simple system where the people who write the rules basically very detailed has to express how the rules should behave. So in a sense, there's not much help from the computer because when you write the rules, says that when this happens, then you have to select this and this and this, and you have to chain them all the way through. So there's not much of a rule engine that will help you in that regard. That changed with the introduction of what's called constraint-based systems, and I've also put some well-known implementations on the right here. In constraint-based systems, you do start to get into more cleverness, that there's a search through the rules to detect and calculate the consequences of the rules. I think what I can say most sort of in these very short time period is that this is very much a search strategy. You go through the rules and you try to deduce information based on what the user has selected, and that also means that the performance and the feedback that they give are quite dependent on how these rules have been expressed in the first place. So they struggle with performance problems, and they struggle with having a difficult time maintaining the rules. And then we came along, and this is, it's 20 years ago, and we found a new way of doing this, and that's what I will spend the rest of this tech talk to present. How did we solve the configuration problem? So, very high level, our approach is a two-phased approach. The first phase, you compile the rules, and compiling it means that you build a representation of all the valid configurations, all the combinations that satisfy all the rules. And once you have that representation, then you use that to do the actual interaction and the guidance to the user. And the benefit of doing this is that, in a way, you could say that this difficult problem, this NP-complete problem, the complex problem, we solve that once, and we do so before we expose before we put the rules out to the user in the configurator. We solve this once as part of the modeling, as when you're writing the rules, just like with normal source code, you compile it before you can run it. It's very similar here. You write your rules, you have to compile the model. Once you have compiled it, you can expose it, and then you can, in the second part, interact with that compiled representation. And this approach has a number of benefits. The most fundamental one is that once you have compiled the solution space, you have solved the difficult problem, so we can provide this fast and predictable runtime behavior. So let's look at, so here's a little example of how this is done. It's a real customer case where we had 8,000 configuration parameters, 10 to the 50 valid configurations, and that still can be represented very compactly in a 3 megabyte representation. So what I want to do now is to take our bicycle example, and I'll try to explain how we do this compilation. And I'll do that by talking about solution spaces. So what I've done here is I've taken the bicycle example. We had the 4 different configuration parameters, and they have a total of 48 configurations. So that's just multiplying the 3 times 4 times 2 times 2. That should give 48. And I've listed them here just in Excel, all the combinations. Now, what we do in the compilation process is that we go through this complete solution space and we reduce it. And the idea is that when you apply the rules, then the rules are basically removing or eliminating some of these total set of configurations. So if you take the first rule here, it says that material, if its material is aluminum, then you cannot have the color equal to blue. So what I've done is I've sort of crossed out or eliminated those rows here highlighted in red. So we can see that all of them share the fact that the material is aluminum and the color is blue. So they are bad rows, so to speak. You cannot pick any one of those. And we do the same with the second rule, and that will eliminate other rows in our solution space. It could have eliminated some of the same ones, but these are all the ones where we have Asia and have something which is not aluminum, so carbon fiber. So what we end up with by doing this is that we end up with the solution space, the actual configurations that are satisfying all the rules, and it's this one. And this is sort of the output of the compilation process. Once we have this representation, this table of the valid configurations, building a configuration application, an application that guides a user, is actually very, very simple. So we can look at this this way. We have a configurator. We have the drop down with the color and region and material and warranty. That's the 4 configuration parameters of our model. Now what we can see is what value should we put in the color drop down? Well, we just go through the column called color and identify the different values that are possible. We can see that there's both a red and a blue and a green. So we put red and blue and green in the drop down. Same thing for the other ones. Now what happens when the user selects a value? Well, now let's assume that we select Asia as our choice for the region. What happens is that we will highlight or all other rows that doesn't have Asia in it, we should disregard, we should eliminate. So we only care about the ones that has Asia in them. And now we do the same thing again. We say, what colors can I have? And we see we can have only red and green. So we get a situation like this. We can only have red and green in the color drop down. What about the material? We notice that we can only have aluminum. Okay, so we only put aluminum in there. The carbon fiber has been grayed out. What about warranty? Well, we can have both warranties. So in this way, building up these drop downs and finding out what is the possible values, that's quite trivial once we have the complete solution space available. So that's sort of the idea here. If we can represent the solution space, doing the interactive configuration is easy. Now, the challenge, of course, is that these solution spaces are very, very big. They are, in a typical case, they are 10 to the 20, 10 to the 30, 10 to the 50. So having a computer, having this Excel sheet, trying to express them explicitly is just hopeless. We quickly get to the number of solutions, which is comparable to the number of elementary particles in the universe, which is like humongous numbers. There's no way we can just store them explicitly. And that's why we call our approach for virtual tabulation, because it doesn't do it explicitly, it does it implicitly. And the background between the technology that we use is called binary decision diagrams. And this is a well-known data structure in computer science. It was discovered in 1986 by a guy called Randall Bryant. You can read about it on Wikipedia. There are books written about it. And this is sort of the data structure that we use behind the scenes. So let me try to spend 2 minutes explaining how this actually works. So the way we do this is that we take, again, our little bicycle example. And the first thing we do is that we take all the values, all the features, color, and the different regions, and we code it up in a binary coding. So we use 2 binary bits, 2 bits for color, B0 and 1, give them some coding. Same thing for the other ones. So this is just to make everything Boolean. So now we can talk about green as being 0, 1. It's 2 Boolean variables. One is 0 and the other one is 1. Then the next thing that we do is that we construct a graph. And I don't have the time to explain how we do this, but the output of the compilation process will be a graph that looks like this. And what this does is that this represents the 38 valid configurations. This is the same information as I showed in that Excel sheet with 38 configurations in it. And the way it does it is that it has nodes, and we'll see that there's a node here, and it points, it has, all nodes has a left pointer and a right pointer. So that's what I try to illustrate here. Each node has a Boolean variable, and it has a dotted line, which is the path to take if that Boolean variable is false, and it has a solid line, which is the path to take if it's true. There are some cases where there's a constant 0 or constant 1, either for the left or the right, and that means that is an illegal. If it's 0, it means that's an illegal choice. In this case, the 0 indicates that B1 cannot be true, because that would be leading to the right hand side, and that's sort of so if B1 is true, then that's an invalid configuration. So let's try to see how this works. And I need to move this out of the way a little bit. Hold on a second. Okay, this is a bit problem. I have a big panel and I need to see where I'm clicking. Okay, so here we see a path, and it goes out on the left side for this B0. That means B0 is 0. That means the color is red or green. We can see that if the first bit is 0, then the color is either red or green, and it goes down to this node. And we can sort of trace that path through the region. That's a true and true, because B2 and B3, it's the right hand side of the node. Both of them have to be true. Then that means that we are in Asia. And then we see that if we are in Asia, so this path here represents that we are blue and in Asia. And you can see here that that means that B4 has to be the left side. It has to be 0, because that's a 1 there. And that means that the material must be aluminum, because that's the 0 for the material here. If we continue this, we can see also that if we are blue, that was this path. And if B2 or B3 is 0, that's the left side, then this goes to a 1, so that's a valid configuration. This is a little tricky, but that's just to give you an idea of how such a graph represents that table with the 38 combinations. If we take this path here, we see that it's a path where we start with B0 being true, going down here, and B1 is 0. So that's the color equal blue, 1, 0. So this is the blue case. The other one was the non-blue case. And when we're in the blue case, then we can see that if we go 1, 1, that's invalid. So we cannot get blue in Asia. And we see that these two paths here means that one of them, either B2 or B3, was 0. And that means that it's not Asia. And then we can see that in that case, we must have a material, this B4 must be true, and that means it must be carbon fiber. So that was my attempt to, in 2 minutes, explain what's inside these VT representations. The clever thing here is that these graphs are very compact compared to listing all the combinations in an Excel sheet. And for example, you will notice that there's no notes in this graph that talks at all about the warranty. It's completely gone. Whereas in the Excel sheet, the warranty was like all over the place. It was a whole column. And the reason that there's nothing about the warranty in this graph is that there's no rules that talks about it. So it's sort of a free variable. So it doesn't have to be included in the graph. If you look at some actual models that we have had over the years, this is some actual models from customers, and you see the number of solutions, the number of variables, how many rules. The nodes and edges illustrates how big these graphs become. So they do become fairly big, 500,000 nodes, 1.5 million edges. But also notice that the size of these solution spaces are quite large. Several of them are above 2 to the 200 or 10 to the 200. So they're very complex and very big configuration models. And you can also see that the size of this VT representation, it's in the megabytes. For these real-sized examples, it's not like trivial, but it's on the other hand, compared to the solution space sizes, it's a very, very efficient representation of the solution spaces. So quickly running out of time here. What can you do once you have a solution space? And I think that's one thing is that you can use it for the interactive configuration, but you can also use it for different types of analysis. And you can make queries, all kinds of queries that you like. You can say things like, give me all the combinations of these particular configuration parameters. And you can do so under a given condition. We can compute that very, very efficiently. It is as if you have the Excel sheet, but you don't actually have it, but you can still make queries about it. You can ask things like, does there really exist a configuration in which this particular condition holds? So across the billions of possible configurations, you can check this type of things very efficiently. You can also ask, is it always the case that if A and B holds, then C also holds? Well, and of course, I've used these abstract terms, but these are all the values and of the configuration parameters that you use. And one of the cases or one of the analysis that we do is to make sure that when you have a bill of material, a configurable bill of material, where you need to make sure that the parts in that and the conditions that are in that configurable bill of material is actually aligned with the configurations that are defined in the product model. And there are different scenarios that you need to deal with. And here I try to illustrate that by showing on the left in blue sort of part of the solution space where we have shown some valid combinations between a configuration parameter called pack with some features down here and seat control. And here we have the bill of material side of things where we pick up a certain part numbered just from 1 to 6, depending on the on the combinations over here. And there are different analyses that you would like to do. One is called under engineering, making you want to discover if there are valid combinations that doesn't have a part which is required. This would definitely be a problem if you, for example, if it was a car and this was the seats, and you would get a configuration, an order that didn't actually drive any seats, and you'll end up with no seats on the car. You can also get into what we call ambiguous parts, which is where you have a ambiguation. You have it's not clear which part to use. Is it this one, or is it both? That can be an error. And the last analysis that we often do is that of over-engineering. This is a situation where you have a part where there is no valid configuration that drives this part. This is the type of analysis. You can do this analysis across all billions of configurations before you even release and deploy the product model for sales, for example, to make sure that everything's aligned. So that was a little bit about VT technology. It's it's difficult to really get into the material in this short time span, but I hope it gave you some insight to what it is when we say we compile product models and we use these VTs to represent the solution spaces. So with that, I will jump directly into questions from the audience.
So I've got one here that asks, can special requests which are not in the solution space be handled?
Yeah, so that's a broad topic of how to handle engineer to order, and there are different approaches, but you can code it in the model to say I want red, green, blue, or special, and then type in your own color, and there are different approaches to do that. But you have to code it up and handle it separately in the order fulfillment processes.
Brilliant. Okay, I've got another one here. You mentioned rule-based, constraint-based, and compilation-based. Is there a migration path available, and how would it look?
It depends, I would say, from what systems. For example, some might know that we can interpret SAP models, and so we can migrate those to VT, but it is something you would have to do on a case-by-case basis. In general, I would say the true constraint-based solvers are fairly easy to migrate because they use what's called a declarative modeling. SAP actually uses a mix, which makes it exceptionally difficult to migrate. But if you do have a clean declarative model, then it should be fairly straightforward to migrate that.
Okay, we are running a little bit out of time now, so I'm just going to ask one more question, and that is, what are the recommended tools to analyze the VT solution space? Can you make an example of a potential output of that kind of analysis?
Yeah, so that there are different toolings on top. We provide some out of the box. For example, you can providing a solution space for certain selected configuration parameters. You might be interested in parameter A, B, C, and D, and we have built in that you can just get that out, and that will produce an Excel sheet, and it will basically have a row for each of those. And then you go, didn't we say that these solution spaces are huge? Well, they are, but if you restrict it down to a small set of configuration parameters, then they're quite manageable, and they're quite useful to link the full configuration space to, for example, a bill of materials. So an engineer can use that to know what combinations he needs to have an engineering solution for in the bill of material. But it can also feature trees, and it can be, we have done different types of statistical analysis on top of the solution space to help optimize and eliminate those combinations that are very unlikely to actually be selected in a configuration process.